The null of A or B? A. It's the set of all x's such that A times x is the 0 vector. Good. And the col of A, B, obviously, it is just the span of the columns of A.
A is R3, I think.
Okay, so let's see. The col of A, remember, col of A is the span of the columns, meaning linear combinations of the columns of A. So if you take a linear combination of the two columns in A here, what the result is going to be in R3. Okay, and then the null of A is going to be a subspace of R2. Yeah, the number of columns. So you can give yourself a maximum of 4. You just had an extra chance to get one of your 4 points today. All right, so I have this like handy little picture here to help remind you what the null of A and the col of A are. If A is an M by N matrix, think of A as the A of a linear transformation that sends x to AX. The null of A is in the domain. It's things that you multiply A by, right? It's a subspace of the domain, and it's the set of all things from the domain that gets mapped to 0. Okay? And then the col of A is a subset of the codomain, and it's actually the range of the transformation, right? All linear combinations of the columns. So that's, and this picture I'm going to add to over the next several classes as we learn more and more vocabulary words. So within these clouds that represent spaces, there'll be more and more stuff. So sort of keep that picture in your mind as we build new concepts. So the null space is just a set of all vectors such that AX equals 0. That's the null space of a matrix A. It's a subset of the codomain, right? And the column space is a set of all linear combinations of the columns of A. Think of it as the range of the transformation T. So both null A and col A are subspaces. Null A is a subspace of Rn, col A is a subspace of Rm. The null space of a matrix is also called the kernel of the associated transformation T. So I could ask you find the null of A or the kernel of T. I'm asking you the same question. Okay. The null of A is just the 0 vector. So if we're talking about the set of things that gets mapped to 0, if the only thing in there is 0, that means that the only solution to AX equals 0 is the trivial solution, which was our definition of being one-to-one, and linearly independent. Okay. And then col A is all of Rm, right? If the range of col A takes up all of Rm, that's saying that the columns of A span Rm, right? So if the col of A is all of Rm, that means AX equals B has a solution for every B in Rm, equivalent to saying the columns of A span Rm, or that the transformation T maps onto Rm. So we just now have a couple of new concepts that kind of mean the same thing as things we've been talking about all semester. Okay, so here's the summary chart on your packet again. So let's look at the demo. So I've got a matrix here. It is 2 by 4. Okay. I would like to know if the vector 1, 4, 2, 5 is in the null space of A. Okay. So what it means to be in the null space of A is that A times the vector should give me 0, right? The null of A is the set of all x's such that A times the x will give me 0, right? So I have to check, does A 0, 1, negative 1, 1, 2, 0, 0, negative 1, that's A, times my vector x that I was given, 1, 4, 2, 5. I want to multiply them together, and if I get 0, then the vector is in the null of A. Okay. I get 0. So this is a 2 by 4. This is a 4 by 1. So my result should be 2 by 1, 0, 0. Yeah. Mm-hmm. They're the same. Yeah. The vertical line and the colon are used interchangeably. It's a good question. Okay, so this means the answer is yes. Okay, if you take your vector, multiply it by A, if you get the 0 vector, it's part of the null set. Or not the null set, the null of A. All right, is 1425 in the call of A? Why not? A 2 by 1. It's the wrong size, right? The column space of A is just all linear combinations of the columns of A, which means if you take linear combinations of those 4 columns, you're going to end up with a vector in R2, right? So this is just impossible. I don't even have to check. No, because call A is a subset of R2. So that symbol means contained in, right? Or is a subset of. It's like a C with a line underneath it. Yeah, yeah. It's used similarly. C with a line. Contained in or equal to R2. So that's definitely a no. We don't even have to check anything. All right. Is 3, 7 in null A? No, why not? It has to have 4 entries to be in the null. So this is a no, because null A has to be contained in R4, has to be a subset of R4. Because you can't multiply a 2 by 4 matrix by a 2 by 1 vector. It just doesn't work. So we can't even check if it gets sent to the 0 vector. All right, how about 3, 7 in the call of A? So this one we'd have to check, right? It's possible because it's the right size. If there's a pivot in every row, how do you know there's a pivot in every row? You gotta look at it. All right, so let's just write out what you would have to do in case you couldn't see it off the bat, right? So I want to know, are there weights that you can put on the columns to create the vector 3, 7? So is there an x? I want to solve ax equals 3, 7. Is there a solution to this equation? So how do I figure this out? Augment the matrix. So my matrix was, I don't remember, 0, 1, negative 1, 1. Somebody read the last 2 columns to me. Thank you. Right, and then augment it with a 3, 7. Row reduce. Thank you. So does this have a solution? Yes, this is consistent. So yes, there are definitely an x that gets sent to 3, 7. There are definitely weights that you can use to create 3, 7. And in fact, there's infinite possibilities because this is has a free variable. So this is yes. Does that make sense? Okay. All right, let's look at number 2. Here I've got a 4 by 4 matrix, and I want to come up with an explicit description of the null space of A by giving a set of vectors that span the null space. So this is probably, I think, Cooper, what you're saying was confusing in the reading. All right, so I want to describe the null space. So I want to write out all the vectors that get sent to the 0 vector. Okay, so I want to know for ax equals 0, I want to know all the x's that do that. Right? So all I'm going to do is augment this matrix with some zeros and solve for the x's. So I'm going to just come up with all the x's that make ax equals 0, because those are the x's that are in the null space. All right, so I'm just going to do 1, 0, 5, 0, 0, 1, 0, negative 2. 0, 3, 1, negative 6. Augment with the 0 vector. And row reduce. Thanks. Okay, this is a 4 rows, 5 columns. 1, 0, 0, 0, 0, 0, 0, 1, 4, 3, 0, 5, 0, 0, 1, 0, and 0, negative 2, negative 8, negative 6, 0. All right, so I go back in here, matrix, oops, math, RREF, A. All right. Okay, so the last thing I have to do, if I was going to write this as the span of a set of vectors, I'm going to put it in parametric vector form. Right, so this is a useful way for us to review parametric vector form. So this one says x1 is 0. This the next row says that x2 plus 4x3 is 0. The next row says that x4 is 0. And my last row says nothing, right? It says 0 equals 0. All right, what is my free variable here? X3, because there's no pivot in that column. So my free variable is x3. So if I want to write out my solutions, right, x1, x2, x3, x4, my solution set is always going to be 0. X2 is negative 4x3. So based on this equation, if you solve for x2, you get negative 4x3. X3 is free, so I'm just going to put an x3 there. And x4 is 0. And now pull out the parameter. Pull out the free variable as your parameter. So I'm going to rewrite what I have here with an x3 outside. It's just like factoring. And I'm going to have 0, negative 4, 1, 0. And that's what my whole solution set looks like. These are all the x's. These are all the vectors that get sent to the 0 vector when you multiply by a. They are multiples of 0, negative 4, 1, 0. Because x3 is free, it can be anything. Okay. So when I multiply a vector times any weight I want, I'm taking the span of that vector, right? So the vector, so the null of A here, I'll write it up here. The null of A is the span of the single vector 0, negative 4, 1, 0. It could be multiple vectors if when you wrote it in parametric vector form, if you had 2 free variables, yeah, then you would have 2 vectors that you're taking the span of.
So a non-zero vector for null A would be 0, negative 8, 2, 0.
Sure. A vector, a non-zero vector in the null of A would be pick anything you want for x3. Chose 2. So we get 0, negative 8, 2, 0. A non-zero vector in the null of A. Yeah, you could do pi, you could do any multiple of that vector. All right, so if I want to find an explicit description for call A by giving a set of vectors that span the column space. So remember, span is the set of all linear combinations, right? So give me a set of vectors that when you take all their linear combinations, you get the column space. It's kind of a straightforward question. Maybe it's too easy. All of R4, only if you know that the column space of A is all of R4. Yeah, well, I'm not sure that that's true. All right, the question's too easy. You're overthinking it. Okay. Yes, all the columns in A, yes. Oh no, you don't add them though. You just list them and take their span. All right, so think about the definition of col A. Its definition is a set of all linear combinations of the column of A, of the columns of A, right? The definition of span is a set of all linear combinations of the things in the set, right? So col A is the span of the columns of A. 1, 0, 5, 0. 0, 1, 0, -2. 0, 4, 0, -8. And 0, 3, 1, -6. The span of those vectors just means the linear combinations of all those vectors, which is the column space of A, right? That's the definition of the column space of A. So that one's super easy. You don't have to do anything at all, right? When I ask you for a spanning set for col A, you just list the columns of A. Okay. Yes. Yeah, you have a quiz on Friday. All right, give me one non-zero vector in the column space of A.
1, 0, 5, 0.
Somebody give me one non-zero vector in the col of A that's not one of the original ones listed in the spanning set. 2, 0, 10, 0, sure. 1, 1, 5, -2, good.
So basically,
Any linear combination of those guys will be in col A. Yeah. Mm-hmm. It's put a weight of 1 on the first vector, 0s on the others. Yep. All right, what do you think? Questions? Okay. All right, so before you jump into the activities, I want to pull up the syllabus and remind you what's coming up. Yeah, you have a quiz on Friday. This Friday. Yep. 3-1, 3-2, 4-1, and 4-2. Okay. It'll be a group part and an individual part like usual.